Uh, so, uh, Good afternoon, everyone. I welcome you all to the last problem solving session for this mathematical methods course. This will be our last session for last problem solving session for this course, and in this problem solving session, we will be covering 8 9 problems from the problem set 12, and as tomorrow is the last date to submit the assignment, so you all guys can go through it once and try to solve problem from by yourself, and then try to solve the assignment. And also your exam is coming on 28th of October, so I will urge you all to do more practice so that you can gain more from the topic. And also I will urge you to try to solve each and every assignment before you go for the exam, as that will boost your confidence and you will have more grasp over the subject. Okay, so let's start with the problem solving session 12 then. So here I will be solving some of the problem from the problem set 12. So let's start with the problem number 1. So so let me just use my laser pointer. So for first question is the Fourier transform of the function fx, which is given as 2t e power minus 2t for t greater than 0. So you need to find the Fourier transform for the given function which is defined from the interval t greater than 0. Okay, so you already know how to do the Fourier transform. So in this problem we will be using just a small trick to solve this problem. So let's see what is that trick. So we are given fx is equal to 2t e power minus 2t for t greater than 0 and 0 for t less than 0, right? Now in your lectures you have learned the property of this Fourier transform. So if the Fourier transform of the function ft is f of omega, then the Fourier transform of t times ft is given by iota df omega by d omega, right? So if you take the function e power minus 2t, right? If you take the function you can choose ft as e power minus 2t, and then your t will be like this only. So basically it is this property is matching with the given question, right? It is of the same form. So basically if you can find the Fourier transform of the function e power minus 2t, then you can get the Fourier transform of this given complete function. So here, as you see, we are choosing ft as e power minus 2t. Therefore f of omega will be 0 to infinity e power minus 2t e power minus iota omega t dt, because that is the definition of the Fourier transform, right? So now you need to know like what is the Fourier transform of the function e power minus 2t, right? So you already know it's very easy to integrate. So it will be integration of this will be e power minus 2 plus I omega, right? So it will be e power minus 2 plus iota omega t, and then in denominator you will have minus times 2 plus iota omega, and you are integrating it from 0 to infinity. Now when you have t is equal to infinity, this whole term will get 0, and then when you have t is equal to 0, you will get 1. So minus and minus sign will get absorbed together to give plus sign, and then you have f of omega is equal to 1 upon 2 plus iota omega, right? Therefore Fourier transform of t times ft, then we can use this property. So basically you just need to differentiate the f of omega with respect to omega. So here f of omega is 1 upon 2 plus iota omega. So the derivative of it, like iota times d of d omega, and f of omega is 2 plus iota omega power minus 1. I can write it like this, and the differentiation of this will give you 1 upon 2 plus iota omega whole square, right? Because here you will get some minus sign and then 2 and then iota square, so that will become positive. So basically you can say the Fourier transform of 2t e power minus 2t will be 2 upon 2 plus iota omega whole square, right? So here we just use the small trick which is known as this property of the Fourier transform, and using this the question become very easy, right? You just need to write the Fourier transform of the function f of t. Okay, so I hope this question is clear to all of you. And uh, here you see how the powerful this property is in order to solve the given question. Okay, then let's move on to the question number 2. So the question number 2 is The Fourier sine transform of the of function fx if fx is given by following function. Fx is sin t if t lies between 0 and 1, and fx is 0 if t greater than 1. So question is saying that you need to find the Fourier sine transform, right? So you already know like what is Fourier sine transform. So what you need to do, Fourier sine transform is represented as fs. So you write fs of fx, and then the function is defined only between 0 and 1, so you have 0 to 1 sin t sin omega t dt. So the Fourier sine transform is defined as this, like ft sin omega t dt. Here ft is given by sin t, so you have this. Now what you can do, you can use the trigonometric properties to write it as 2 sin a sin b. So to do that, I need to divide it by one more 2, so that I can write it in this form, right? And then I am using the property of 2 sin a sin b, so that will be cos a minus b minus cos a plus b, right? So cos a minus b will be t minus omega t, and minus cos a plus will be t plus omega t, right? And integration from 0 to 1. Now the integration of this will be integration of cos t minus omega t will be sin 1 minus omega t upon 1 minus omega. Similarly here you have minus sin of 1 plus omega t upon 1 plus omega. So here I am just doing the normal integration of cos function, and then you integrate it from, and then you put the limits from 0 to 1. Now when you put t is equal to 1, right? So if you have t is equal to 1, you have sin 1 minus omega upon 1 minus omega, and here you will have sin 1 plus omega upon 1 plus omega. And when you have t is equal to 0, then this both of the function will become 0, because sin 0 is 0. Therefore the Fourier sine transform of the given function fx, which is given as sin t between the interval 0 to 1, is given by half times sin 1 minus omega upon 1 minus omega minus sin 1 plus omega upon 1 plus omega. Okay, so I hope this was again a very simple problem. Here I just use the Fourier sine transform definition to do the following question. Okay, then let's move on to the problem number 3. So using the Fourier transform, the solution yt of the differential equation y dash minus 4y is equal to u naught t e minus 4t, right? So basically you need to use the Fourier transform, properties of Fourier transform, in order to find the solution of the following differential equation, right? So as you did earlier, like when we were solving some Laplace problem, there also we took the Fourier transform on both the side, right? So Laplace transform on both the sides. So here what you will do, you will take the Fourier transform on both the side. So let's see how to solve such problem. So what you do, you have given y dash minus 4y is equal to u naught t times e minus 4t, right? That is given. So now what you do, you take the Fourier transform of both the side, right? So as you know, using the derivative property of Fourier transform, if Fourier transform of y of t is f of omega, then the Fourier transform of y dash will be iota omega f omega, right? Minus 4f of omega, because here the Fourier transform of y of t will be f of omega, and then the Fourier transform of u naught t power minus 4t, which is a general equation. The Fourier transform of that can be written as 1 upon 4 plus iota omega. So if you don't remember this, then recall our last problem session also. There also we use the following property in order to solve such problem. Okay, so here I did nothing. I just took the Fourier transform on both the side, and then I used the derivative property of the Fourier transform, right? So now from here what you can do, you can find the what is the value of f of omega, right? So the value of f of omega will be 1 upon 4 plus iota omega times iota omega minus 4, right? So here I have taken iota omega minus 4 and f omega outside, and then I can write f omega in this form. And now it can be written as f of omega is minus 1 upon 4 square plus omega square, right? Because if I just do the multiply this both the expression, then I will get minus 4 plus square plus omega square, right? So minus sign is coming here. Now what you need to do, you then need to do the inverse Fourier transform, right, in order to have the solution y of t. So here f of omega you can also write, if I write it as, if I multiply 8 in the numerator and denominator, then I can represent f of omega as minus 1 by 8 times 8 upon 4 square plus omega square, right? Just simple form to write it. And then if you recall, like what is the Fourier transform of e power minus 4 mod t, right? So if you try to find the Fourier transform of e power minus 4 mod t, then you will get 8 upon 4 square plus omega square, right? So basically, you know the Fourier transform of e power minus 4t, and then you also know like what is your f of omega, right? So if you take the inverse Fourier transform of both the side, right? So what you will get f of t is equal to minus 1 by 8 e power minus 4 mod t, right? So here I have just used the following property of the Fourier transform, where I already know like what is the Fourier transform of e power minus 4 mod t, and from there it's very easy to back calculate like what is the function f of t, right? From here, so minus 1 by 8 was outside, and then I have uh, the following term. Okay, I hope it was again a easy problem, and you see the power of the Fourier transform, like how it can be used to solve some differential equation. And I will urge you to redo this problem, as this problem is not in the assignment, and you may get it somewhere in future. So I will urge you to try this problem by your own, and do more practice. Okay, let's move on to the next question then. It was also a fairly easy question. So here you need to use the convolution theorem of Fourier transform in order to find the inverse Fourier transform of the given function. Okay, so here I hope you already know the such type of problem. So but let's, for the completeness, let's just go through the solution. So here given f of omega is given as 1 upon iota omega plus 2 whole square, right? So I can write it as 1 upon iota omega plus 2 times iota omega plus 2, right? So this is just a simple expression which I have written like this. Now if you recall the properties of the inverse, so I can write it as f inverse f of omega, and then I can write it as f inverse of h omega g omega, right? Where I am calling this function as h and this function as g, and h of omega is equal to g of omega because both of the functions are same. Now if I ask you what is the inverse Fourier transform of h of f of omega, right? So you already know, like if you take this function which is 1 upon iota omega plus 2, then the inverse Fourier transform of this is given as e power minus 2t u naught t. Recall this, we also did this here, like same expression, right? Here like u naught t power minus 4t is 1 upon 4 plus iota omega, but if you have u naught t power minus 2t, then it will be 1 upon 2 plus iota omega, right? So here it will be e power minus 2t u naught t. Similarly for this you will have f inverse g of omega is equal to e power minus 2t u naught t, right? Same, because both function are same, so their inverse Fourier transform will be same. Now if I use the convolution theorem, so what does convolution theorem say? Convolution theorem says that f inverse of h omega g omega is nothing but the convolution of their function, right? So here f inverse of f of omega is nothing but the convolution of both of these function, right? So if I now apply the convolution theorem, it will be minus infinity to infinity e power minus 2 tau u naught tau times e power minus 2 t minus tau times u t minus tau d tau, right? This is just, I have used the convolution formula, right? Now you already know like u naught tau is nothing but a step function, right? And then you have two step function here, which is u naught tau and u t minus tau between minus infinity to infinity. Now if you recall the property of this step function, then u naught tau and ut minus tau is equal to 1 if t lies between 0 and tau, and 0 otherwise, right? So this you have also done in class, the same thing, where you use this formula of the step functions. Now what you can do, you can write it as f inverse of f of omega, and here you know u naught tau times ut minus tau is 1, right? For interval 0 to t, and then e power minus 2 tau and e power 2 tau will get cancel each other, then you will have just left with e minus 2t, right? So you have integration 0 to t e power minus 2t d tau, right? And the integration of this is nothing but t e power minus 2t, right? Because e power minus 2t is independent of tau, so you will just get tau here, and then when you put the limit you will get t times e power minus 2t. Therefore the inverse Fourier transform of 1 upon iota omega plus 2 whole square is nothing but t times e power minus 2t. Okay, so I hope this question was also very easy. So here we just use the convolution property of the convolution property in order to solve the inverse Fourier transform. So I urge you to remember this property, as this sometimes this property is useful in order to calculate some inverse Fourier transform of some functions. Because if you have some other function like iota omega plus 2 and iota omega plus 3, then also you can use the following property in order to solve such functions, such questions. Okay, so this was all about this problem. So now let's move on to the next question then. So the next question is, next question is a like a good question. So here question is saying you need to use the Fourier cosine transform of e power minus x to calculate the value of this integral. Okay, so basically you need to write the Fourier cosine transform of e power minus x, and somehow you need to put it in this form so that it will give you the integration value of the following function. Okay, so let's see how to do that. So first of all, if you recall the for Fourier cosine transform, I can write a omega is equal to 2 times 0 to infinity e power minus x cos omega x dx, right? So this is, I am like using the expression from the lectures for the Fourier cosine transform, where you can write a of omega is equal to 2 times 0 to infinity e power minus x cos omega x dx, right? Now if you use the following integration property, which is e power minus ax cos sx dx is given by e power minus ax upon a square plus s square times minus a cos sx plus s sin sx, right? So here the value of a is 1 and the value of s is omega. So if I do that, I will get a omega is equal to 2 times e power minus x upon 1 plus omega square times minus cos omega x plus omega sin omega x, right? So now the limits are from 0 to infinity, right? So if I put x is equal to infinity, I will get 0 because e power minus infinity is 0. And if I put x is equal to 0, I will get this will get 0, this will give minus 1, and then minus minus will get plus. So I will get 2 times upon 2 upon 1 plus omega square, right? Now also if you recall, a omega can be represented as 2 times of fc omega, where fc omega is nothing but the Fourier cosine transform of the given function. Okay, so basically now I know what is a of omega, right? So you know what is a of omega. So a of omega is 2 upon 1 plus omega square, right? So now what you can do, you can again use the following property where you can back calculate. So if you write how you can write fx is in terms of cosine transform, right? So fx, again you can watch the lecture and there you will see like you can write fx in terms of 2 by pi 0 to infinity 1 upon 0 to infinity, then there is fc omega here, f of c omega, right, times cos omega x dx. So here I am just back calculating the given function, right? So here you know, like here I have written fc omega times cos omega x. So fc omega was nothing but a omega by 2. So a omega by 2 will be 1 upon 1 plus omega square, right? So here now if I put fx is equal to e power minus x, right? This you already know, like what is fx. So the integration from 0 to infinity cos omega x dx upon 1 plus omega square can be written as pi by 2 times e power minus x, right? Therefore the integration of the following function from 0 to infinity, where function is cos omega x upon 1 plus omega square dx, can be written as pi by 2 times e power minus x. Okay, so here this question was actually a very good question, and again I will urge you to try this question by yourself once, and and so that you can get more practice on the different questions of the Fourier transform. So here you see the powerfulness of this Fourier transform, which can be used to calculate this complicated integral, which is cos tx upon 1 plus t square dt, right, from 0 to infinity. And the value of this integral from the Fourier transform can be written as pi by 2 times e power minus x. Okay, So I hope this question is again clear to all of you. So I will move on to the next question then. So here the question is the Fourier cosine transform of fx if fx is 1 plus x. Okay, so here you again need to calculate the Fourier cosine transform. It is like a previous question, before that, and then you need to just write the Fourier cosine transform of the given function. Okay, I hope this is easy question, so I will just go through the solution. So the Fourier cosine transform of fx can be written as 0 to 1, 1 plus x cos omega x dx, right? This you can write, and then you can write you can separate it and write cos omega x times x cos omega x dx, right, from 0 to 1, because function is defined in interval 0 to 1. And then you know like what is the integration of cos omega x, so it will be sin omega x upon omega. And for the second part you can apply integration by parts, right? So you can choose x as first function and cos omega x as second function, and then you will get the following value of integrals before putting the limit. So now you can put the limit from 0 to 1 in all of three expressions. So if I put x is equal to 1 here, I'll get sin omega upon omega, and if I put x is equal to 0, I will get 0. Similarly, if I put x is equal to 1 here, I will get sin omega upon omega, and if I put 0, I will get 0. Similarly, if I put 1 here, I will get cos omega upon omega square, and if I put 0, I will get 1 upon omega square minus sin. So basically the Fourier cosine transform of the function f of x can be written as, so here what I can do, I can take omega square outside, right? So 1 by omega square outside I can write, and then these and this are same, so it will give me 2 omega sin omega, right? Because here I have only 1 omega. So when I take omega square common, then 1 omega will go into the numerator. So I will have 2 omega sin omega plus cos omega minus 1, because both these expression has omega square in the denominator. Okay. So I hope this question is again clear, and this was a fairly easy question. So now let's move on to the next question then. So the next two question I have taken from the boundary value problem. So and those questions are typically from the assignment number 12 only. So I just picked only two, because I realized like covering these two questions only will give you like you can solve any other question if you know those two. Okay. So let's start with the first problem. So here you are given the using the Fourier transforms the solution uxy. So you need to find the solution uxy of the given partial differential equation, right? Which is d square u by dx square plus del square u by del y square is equal to 0. And then you are given two boundary condition here. So basically you have del u by del y is equal to 0 when x at x comma 0, and then you have u x comma 1 is equal to e power minus 2x. So first of all you need to decide in this question like what thing you will use. Okay, so looking at this, if you see the x is varying from minus infinity to infinity, and the interval of y is bounded. Okay, so what you will do, as x is from minus infinity to infinity, then you need to use the normal Fourier transform here. And you will use which variable? So here you will use x variable here, and you will use the normal Fourier transform. Okay, so why in terms of x? Because x is ranging from minus infinity to infinity, and also this as x is not like 0 to infinity or minus infinity to 0, then you need to use the normal Fourier transform. Okay, so let's see how to solve such problem. Okay, so first of all, this is the given problem, and these two are the given boundary condition. So basically what you need to do first, as you have chosen like I will define Fourier transform with respect to the x variable, right? So now if you write this and you take the Fourier transform both this side, so first of all let's take del square u by del y square, right? So as you are not choosing y as your Fourier transform variable, so this will be del square f by del y square, where f is nothing but the Fourier transform of the function uxy. Okay, now here as you are choosing your variable as x, then you need to use the derivative property of the Fourier transform. So the double derivative property of Fourier transform can be written as plus iota omega square times f is equal to 0. Okay, so basically from here I have written del square f by del y square, and for this I have used the derivative property, so I can write it as iota omega square times f is equal to 0, right? So this is your differential equation in terms of f, right? So now you can write it as d del square f by dy square is equal to omega square f, where you can take this function on the right hand side. Okay, now the solution of such differential equation, as you already know, can be written as a cos hyperbolic omega y plus b sin hyperbolic omega y, right? Again, this is a straightforward where I have just written the solution f, which is a function of omega and y from for the given differential equation. Okay, where I have taken the first the Fourier transform both the side in terms of variable x, and then I have written the form of f, right? So now what you need to do, you just need to calculate these two constant a and b, and then you will get your function f, right? So first of all, if I see this property, so first property is del u by del y x comma 0 is 0, right? So here the variable is we have chosen is x. So here you are given this in terms of y. So basically what it's saying del f upon del y is 0 at x comma 0, right? So basically if you take the differentiation of this with respect to y, and then you put y is equal to 0, then you will get one boundary condition. Okay, so let's see how to do that. So basically you write del f by del y is equal to 0 at y is equal to 0. So if I take the differentiation, I will get omega a sin hyperbolic omega y plus omega b cos hyperbolic omega y is equal to 0 at y is equal to 0. Now if I put y is equal to 0, so basically if I put y is equal to 0, then this part will get cancelled. So basically because sin hyperbolic will be 0, and here you will left with b is equal to 0, right? Because cos hyperbolic 0 is 1. So basically from here you can say my b constant b is 0. Okay, so basically if our b is 0, then our form remains only a cos hyperbolic omega y, right? So basically we are left with a cos hyperbolic omega y. Now you just need to find the value of a, and for that you need to use the another boundary condition, right? So the another boundary condition is u x of 1 is e power minus 2 mod x, right? So basically you can write f of omega 1, right? Basically if you do take the Fourier transform of both the side, right? So you can write it as f of omega 1, right? Because the Fourier transform of ux1 will be f of omega 1. So you can write f of omega 1 is equal to a cos hyperbolic omega, right? And f of omega 1 is nothing but integration minus infinity to infinity e power minus 2 mod x e power minus iota omega x dx, right? This I have just taken the Fourier transform on both the side, as you have done in class problems or assignment problems. So here I can write a cos hyperbolic omega is equal to, and now you need to, as there is a mod here, so you need to break it into two parts. So either you can write minus infinity to 0, and in this interval your mod will be negative, so you will have e power 2x times e power minus I omega x dx, and from 0 to infinity your mode will be positive, so you will have e power minus 2x times e power minus iota omega x dx, right? So if we now able to solve this integration, then we can get the value of a, right? So let's see how to do that. So basically a cos hyperbolic omega can be written as the value of these integrals. So the value of these integral after putting the limits will be 1 upon 2 plus 2 minus I omega plus 1 upon 2 plus I omega, and this is straightforward. I have just take the integration and put the limits in the following two functions. Now from here the value of a can be written as, so if I now take the LCM here, I will write 4 upon 4 plus omega square. So I have multiplied 2 minus iota omega with 2 plus iota omega, and then I have taken cos hyperbolic omega in the denominator. So basically now using the both the properties of the boundary condition, you are able to find the exact form of f. So basically f of omega y can be written as 4 upon 4 plus omega square times cos hyperbolic omega y upon cos hyperbolic omega, right? Because the value of f is a times cos hyperbolic omega y. So basically the value of a can be written as this. So basically the whole function is 4 upon 4 plus omega square times cos hyperbolic omega y upon cos hyperbolic omega, right? Now you, if you know the function f of omega y, then you can back calculate the function ux of t by writing it as 1 upon 2 pi integration minus infinity to infinity f of omega y. So here it will be omega y times e power iota omega x d omega. This is nothing but to write the inverse of this to find the ux of t, right? So now the value f of omega y you already know, right? So this is this value. So what I do, I can write uxt is equal to 1 upon 2 pi integration minus infinity to infinity 4 upon 4 plus omega square cos hyperbolic omega y upon cos hyperbolic omega times e power iota omega x d omega, right? So now you already know, if you carefully see like your function f of omega t or f of omega y, your f of omega y is nothing but a even function, right? So what I can do, I can write this e power iota omega x cos omega x plus iota sin omega x, right? And integration is on omega with limits minus infinity to infinity. Now if you see, your f of omega is even and your cos omega is also even, but your sin omega is odd. So basically if you try to find the integration of this, the only term survive is that of cos omega x, right? Because the sin omega x, when it get multiplied with f of omega t, will get 0, will be a odd function, and this integration from minus infinity to infinity will be 0. So basically I can write ux of t is equal to 1 by 2 pi minus infinity to infinity 4 upon 4 plus omega square times cos hyperbolic omega y upon cos hyperbolic omega cos omega x d omega. Okay, so this is the final solution of the given question. So here again this is a very important question. So first you decide like what to use here. As x is from minus infinity to infinity, you will use the normal Fourier transform, and then you will see how to use these limits. So first of all, as you have chosen the variable x, so this will be just del f upon del y, right? That's why you just take the derivative first of the f, and then you try to find one constant, and that is 0 here, and then you try to use the other boundary condition by taking the Fourier transform on both the side, and from there you got the value of a. So the value of a is this, and then it's really easy to back calculate the function uxt in terms of the following integral. Okay, so I hope this question is again clear to you, and this assignment was from the this question was from the assignment. So I urge you to try this once by yourself and see if you are able to do it or not. Okay. Okay, then let's move on to the next question, last question of this problem session. Okay, so last problem is, if del u by del t is equal to del square u by del x square for x greater than 0 and t greater than 0, where ux of 0 to t is 0 and ux 0 is x if x lies between 0 and 1. So then you need to again write uxt by doing the back calculation in terms of this, right? And then you need to find the value of f of c at omega is equal to 2 pi. Okay, so first of all, you are given the boundary condition of some derivative which is del u by del x, right? And also the Fourier transform variable is x. So basically, and also x is defined for the interval greater than 0. So what you need to use, you need to use the Fourier cosine transform here, right? So what you do here, uh, right? So you use the Fourier cosine transform. So if you write the Fourier cosine transform both the side, here you will have del fc omega t upon del t is equal to minus omega square fc omega t, right? Because you are taking the Fourier transform with respect to x variable, so you will get, using the derivative property, you will get minus omega square fc omega t, right? And now, so you have this differential equation. So from there you can just do the integration on both the side with respect to fc and with respect to t. So you will get fc omega t is equal to some constant which I am denoting as c of omega times e power minus omega square t, right? So here we have already used one boundary condition which is this, right? So now for the, so here you just need to find the value of c omega to get the complete expression of fc omega t, right? And for this what you do, you again take the Fourier cosine transform on both the sides. So if you do that, you will get ux comma 0 cos omega x d omega is equal to 0 to 1 x cos omega x dx, right? Here we, like, what we do for such question, we just take the cosine transform or sine transform or normal Fourier transform on both these sides. So in earlier problem we took the normal Fourier transform. In this problem we are taking the Fourier cosine transform both these sides. So if I do that, this is nothing but fc omega 0, right? This is nothing but fc omega 0. So basically if I put t is equal to 0 here, this correspond to value c of omega, right? So therefore if I solve this integration x cos omega x dx again by using by parts and putting the limit from 0 to 1, I will get sin omega upon omega plus cos omega upon omega square minus 1 upon omega square, right? And therefore fc omega t is nothing but sin omega upon omega plus cos omega upon omega square minus 1 upon omega square times e power minus omega t square t. Why? Because this value, as I told you, is nothing but c of omega, and c of omega can be represented as sin omega upon omega plus cos omega upon omega square minus 1 upon omega square, right? So therefore now you know the value of fc omega, right? So basically the fc omega is sin omega by omega plus cos omega by omega square minus 1 by omega square, right? So if I am this I am matching with the given problem. So you have this fc of omega and e power minus omega square t. So basically I am separating this e power minus omega square t outside. So by mapping to the problem, I will have fc omega as sin omega upon omega plus cos omega upon omega square minus 1 upon omega square. And this is nothing but, the question is asking the value f of c at 2 pi. So if you put omega is equal to 2 pi here, right? So if I put omega is equal to 2 pi, then sine 2 pi is 0, right? Sine 2 pi, sine of any pi is 0, even or odd. Then cos 2 pi will be 1. So you have 1 upon omega square. 1 upon omega square where omega is 2 pi. So you have 1 upon 4 pi square, and then you have minus 1 upon 4 pi square. So if you take the whole value, then this will be 0. Okay. So again, this was again a boundary value problem where you first realize like what to use here. So here you see we use the Fourier cosine transform, as the boundary condition were given like that, and also the transform variable was defined from x more than 0. and and in the earlier boundary value problem we use the normal Fourier transform, as it was defined as x was defined from minus infinity to infinity. Okay, I hope this question is again clear to you all. So this was again the 10th question from the given problem, problem set 12. So, and also this problem was again from the problem set 12. So I urge you all to try all of these problem by yourself, and also do the problem set by yourself. And as tomorrow is the last date, so uh, uh, and also you this is last problem solving session. So uh, I wish you all the best for your given exam, and it was really a nice thing for me to take these problem sessions, and I hope I was able to help you a little with your problem sets, and also in solving your assignments or in any problem you are having. Okay, then I wish you all best of luck for your future and for your given exam. So with this I will conclude with this problem set, as well as the problem sessions for the given course. Okay, so okay, thank you very much, have a nice day.